Are you ready to make that scientific leap? Let's get these three concepts, these three measurable things, clear. A little bit tricky. We got to think carefully. The only way that we can have a revolution is to think carefully, to look carefully like Brahe, to measure carefully, to think carefully. What do we mean by these words? Okay, so by the way, Newton was born in 1642, 43, and then what was going on in the USA? Was it the USA yet? Was it the United States of America yet? What was the Constitution? 1700, what was going on? How did this way of thinking beyond authority affect our Constitution? Very powerfully, big connections, a lot going on. All right, to understand these laws, you need to understand what accelerate means. Now, most people, you say accelerate, you say increase speed. That's the common use of the word accelerate. But in science and in this context, what we mean is broader. So to accelerate, hence Ducati, you can think of motorcycles and you can think of cars if you want to think of accelerating. But notice that a car or a motorcycle can change motion. How many ways? 3 ways, right? So you've got 3 ways to change motion. You can do what? You can increase speed. You can, of course, decrease speed. Decrease speed is called deceleration. When you say decelerate, you mean to decrease speed. But now, in this new way of talking and thinking, accelerate means increase speed or decrease. If you're decreasing speed, that is accelerating. I know it's funny, right? But we need that. And then additionally, how else can you change your motion? I can go faster and faster, I can go slower and slower, or I can change direction or turn. Okay, so that's what that word means. Just think of the 3 ways you can change your motion in a car or a motorcycle, whatever. Keeping that in mind, well, how much is your acceleration? Notice that if you have a large acceleration, like you hit the gas pedal hard, I mean, some cars you hit the gas pedal hard and it still just goes, my first car, forget about it. Hit the gas pedal hard, it's like, but you know, if you got a Ferrari and you hit the gas pedal hard, you're gonna have a large acceleration. If you hit the brake hard, you can have a large acceleration. If you crank the wheel hard, you can have a large acceleration. And so we say a large acceleration is an abrupt change, right? You go, oh, or you stop and you go, oh, you go, ah. Right? Turn this way, you go, oh. You feel it. Small acceleration is a gentle change. Much safer, right? That's going to be safer. This can be dangerous. Someone was trying to set the world record in, was that outside London? Just recently, he was only 47 and he died just recently. It's dangerous, right? It takes a lot of skill. You know, yeah, anybody can step on the gas hard, anybody can step on the brake hard, anybody can crank the wheel hard. But training to be safe is dangerous. So acceleration is what we feel. We really feel it. If it's a gentle acceleration, you might not even, if you're in the passenger seat and you're sleeping, you might not feel that. But if you go like that, you're going to wake up. That's why we don't feel Earth move. It's actually a gentle acceleration because even though we're spinning, it's a very big turn compared to the size of us. It's a big, gentle turn. Okay? That's what we feel. But what causes acceleration? What causes acceleration? Well, before we do that, let's think about things. Let's just look around. So here, if I take this, Is it accelerating now? See, just use this as your guide. When I let go, did it accelerate? Did it go faster and faster and faster? Well, if something falls farther and farther and farther, it's going to hurt more and more and more, right? What about as I push it up, is it accelerating? I start here, not moving, and then I go faster and faster and faster. Then I let it go, think in slow motion. What's it do once I let it go? It goes slower and slower and slower. Stop. It doesn't stop and sit there. That's tricky. We won't worry about that. It's actually still changing. Only momentary stop, and then go faster and faster and faster. Decrease speed, stop, increase speed. What's causing that? How come when I let go, things go faster and faster and faster? What's causing that? If this was a galaxy, then I'd be incredibly big. Galaxies spin. We're about halfway out in our galaxy, barred spiral. Are we accelerating? Are we increasing? We're definitely turning. So whether or not the speed's changing, we are turning, right? Cool. We're going to talk about this. Something driving around on a track. You drive around on a track, making a corner. Are you accelerating? I can increase speed. I can decrease speed. I can keep the same speed. I'm still turning. That's accelerating. That's changing motion. Now, Aristotle thought things out in the heavens just kept going in perfect circles because that's just what they did. We're going to look at a new way of thinking. Okay. And this will apply to Earth, the planets, all kinds of things. This is how we unveil much of what happens. All right, so that's acceleration. Any of those things, and you just have to see it. If you see it, you'll know it's accelerating. You can just watch it. It's increasing speed, decreasing speed, or turning. It can be abrupt or gentle. But what causes it? Check this out. There's a pendulum. Hopefully you can see that. I don't know what's better, from me or it. Is it accelerating? Can you imagine slow motion? What's it doing? What kind of accelerating? Which of these three ways? As I let go? Faster and faster, faster. Slower and slower and slower. Faster and faster, faster. Slower and slower and slower. Changing speed, but also turning. And in fact, usually when you go into a turn, you might decrease speed. And as you go out of a turn, you might increase speed. So all those, so that's it. No, don't make too big a deal about it. All right, that's acceleration. But what causes acceleration? We're going to get into this in Newton's laws. Let's take a look here. All right, cool. A force. Force is a push or pull of any kind. Now, I can push something, right? Or I can pull something to me. But there are lots of kinds. Let me show you that. How strong you can push gently or hard. How strong it is measure in pounds. Libra or balance. Equilibrium, we'll talk about that. LB, Latin. Pounds, given the symbol for Libra, balance. Or newtons. Hey, that's appropriate. Now, if I asked you which is more, a newton or a pound, I think I would guess. No one bothered to ask back in the day. I think newton sounds more impressive, but it's actually about a quarter pound, a little less than a quarter pound. If you order a quarter pounder and you get a newtoner, it's even less than a quarter. You got ripped off. Newton. Anyway, that's how strong. You can push more strong or weaker, right? So that's how much. And there's a direction, right? I can push that way, I can push that way, I can push that way, I can pull this 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 way, right? We're going to get into that. This is key. Super tricky part here. It has to be from one object on another. If all of a sudden I just sped up, I look for who pushed me or who pulled me, right? If it just happened, that'd be creepy. But there's something funny about this, right? You've got to blame someone. And that idea leads to some surprises. You must, well, we're going to get to that. You must blame someone for a push or a pull. Someone pushed or pulled you on another object. And there are many types of forces. Let me show you this, and then we'll explore a few examples. So usually it's from touching. If I'm going to push the board, I got to reach out and touch it. I can't just go, ooh, go. You know, I got to push it. If I want to pull it, well, I need something to grab onto. If I want to pull something, I reach out and grab it, and I pull it. Pull it. Push it. If it's moving there, I can push it to the side. I can pull it, whatever. Right? So from contact. And there are lots of types. So for example, the roughness of a surface. There's actually, even on a smooth surface, there's little grooves, little bumps. Right? And those bumps create what we call friction. Even on this side, which is much smoother, less friction. But there's still some friction. And so when I slide things, they'll stop. So friction is one way. There's a long list in the text. How else? Let's see, a string. Well, look at that. You see, this is the carrot we need. This ball right here, I don't know which way you can see it, here or here, it's being pulled by the string. I am not pulling that ball. Sure, if I didn't pull the string couldn't pull the ball, and so on. But that string is pulling the ball. I'm pulling up on the string is pulling up on the ball. That's the care we need. Okay, a string. How about a spring? Sure, right? And if I notice that, and you could attach that spring to your lip if you don't get it, you just pull. And the more the spring stretches, you can feel it, I can feel it pulling back on me, the stronger the pull. So a little stretch, I get a little pull. If I stretch it more, it's going to be a stronger force, right? Which way? Towards me, watch. Ah. Right? So springs pull, stretchy things pull. And they're touching. You can tell what's pushing or pulling, whatever's touching. Now, the more this stretches, the stronger the pull. You can see that bend. Notice that the stick is actually pulling back. We're going to talk about that. The atoms are holding together, and that has a little elasticity or stretchiness to it. So there's a whole bunch of contact forces that we say. I mean, watch this. If you put this on a surface, see that? Again, I'm not pushing on this thing. I'm pushing on the board. This board here, this wood, is pushing up on that. How do I know? Well, if it fell off, it would go down. That's weird. I could also see it if the board is, I can see it flex. That board is pushing on it. There's different kinds of forces, and in physics, that was what we study, and Newton did physics. Right, so this is a little bit of physics. All right, so those you can tell. You can see who to blame, what to blame, if it's touching you, friction, etc. Right, etc. But this is the weird thing. There are pushes or pulls that can happen without touching. Now, like in the 70s, where people were into like, ooh, I can move things with their mind. People stopped doing that when you got video and you can record them. Also, a lot of the illusionists that are great, some great folks, Chris Angel, Blaine, and they're not saying they can do it. It's like, you figure this out. Here, figure this out. The Amazing Randy, I think I might have mentioned, you can look at, can you move things with your mind? Well, no one's done it, right? They've set up tricks and tried to fool people and take their money. But there still are very weird forces that happen without touching. Some object pushes or pulls another object without touching it? What is that? Now, the most evident of all these is what? Magnetism, right? It's not touching. Can you see that? I hope you can see it. That's so weird. Doesn't he? So out pulls. And it even pushes. It's so cool. Yeah, I could do this all day. Like, how does that work? Well, if you study physics, and who knows, maybe I'll break out a t-shirt. After this in the 1800s, the laws of electricity and magnetism were revealed. Check this out. This is kind of fun. Magnets. Right. Wait, I dropped it. It should fall. Ugh. Don't want to get pinched there. Okay, let's try this one. Ready? Oh, wait. That didn't play. That was brass. How about copper? Does it play? How about aluminum? Does it play? Iron and nickel, some other little bits, but how about wood? Does it play? No, it doesn't play. So why does iron play? Iron's going to be a big, big player in astronomy, huge player in astronomy, as is magnetism. Magnets can push or pull without touching. What? There's also the electric force, and you've got that list in the book. Why does this fall? Aristotle said to go home, kick back, watch the game, or something like that. Galileo said, I don't know, take these cannonballs, I drop them off the Tower of Pisa, which wasn't leaning yet, or was, I don't know. And I don't know about that. Remember, Newton picked up where Galileo left off and took it further. Oh, check this out. This is fun. Can you see this? Watch. Without touching. I mean, it's crazy. It is crazy. You shouldn't just go, oh yeah, magnets. No, it's crazy. There's a push or a pull without touching. I'm not one side it pushes away, the other side it pulls. Whoa, I'm sorry, that's just too cool. I'll stop. Electric force and the force of gravity. And then you can know, okay, there's a force that's happening without touching. There's two more. Inside the nucleus, the center of an atom, there's a force called the weak force, which isn't very strong. And a strong force, which isn't very strong until you get really close, and then it's strong. So those are other types of force. In fact, there's only 5 kinds, but they're actually connected because electricity and magnetism were connected anyway. So you might hear 4, and then known how the connection was with the weak force. And so people explore this, but we don't know how they're all connected. So it's crazy. Anyway, pushes or pulls. Pushes or pulls. You know what accelerate means? To change motion, increase speed, decrease speed, or turn. You can see that. You can say, oh, that's accelerating. It's not accelerating if it's going same direction, no turning, same speed. It's not accelerating. Force is a push or pull. That's a little tricky because, you know, you could see some forces, but other ones are a little tricky. Check it out. If I go like this, my keys. Okay, I am touching and pulling on my keys up here. That part right there. I'm not pulling on these guys. That metal is pulling them up. Something's pulling it down. How do I know? So I pull up here, and that pulls there, and this pulls. So there's all these forces going on. What about these guys? Oh, one of them has some iron. One of them has some iron in it. Okay. We are rolling, and now let's do mass. That's it. Pushes or pulls, forces. See them around you. You can see whether or not if something's accelerating just by looking at it, how it's moving. And then finally, let's get this right, shall we? And respectfully correct people. Let's respectfully correct people. Mass. It's trickier than people want to say. Trickier than people want to say. Okay? Mass is measured, we talk about kilograms. You can talk about grams. Kilograms is 1,000 kilograms. And a gram is not much at all. So, I don't know, a dime or something. People, textbooks, even university, people say mass, to try to make it easy, I guess, is the amount of matter. That is wrong. Wrong. It misses the depth and the point. Now, it's true. If you have more matter, more stuff, here I got 1, now I got 2. You have more mass, but what's more mass? What's mass? What's it got more of? If I have more, oh, I got more mass. What do you mean? If you have more people, you have more ideas. So I got more ideas, but what are ideas? They aren't people. They aren't how many people. I got 3 people. So I got more ideas than if I just had 1 person. Reasonable. But what's an idea? If you got more people, you probably have more shoes. But people aren't shoes. Right? So if you have more matter, solid, liquid, gas, you have more mass. But what is mass? You haven't said what mass is. It is a property of matter, not light. So light has its properties. And Newton wondered about it. Like, wow, what is that? You know, and he did things, but he died not knowing very much. He wondered about things, did set up some experiments and stuff like that. What is light? Turns out to be tricky. We really need Einstein to come in here in the early 1900s, but this set things going, right? So, what is matter? It's a property of matter responsible for 2 things. So if you have more mass, if you have more matter, you will have more mass. But what is that? Oh, mass we measure as how much it resists accelerating. Accelerating. Right? How much it resists. How can we accelerate? Of course, you know this. You already did this. Increase, decrease, or turn. Right? Try pushing that kid in the book on a roller skate. Right? They fly right off. If they're coming towards you, you can save them. Right? If you want, you can send them away. If they're going past you, you can turn them. They're pretty easy. I do it all. No. Try doing an elephant on a skateboard. They're hard to increase the speed. Ugh. If they're coming at you, they're hard to decrease the speed. And you want to make them turn? Ugh. Just get out there on the football field. More mass is harder to increase speed, decrease speed, or turn. We call that inertia. It's like, I can't get going. But also it has to do with I can't stop. And I can't turn, I can't change at all. That's one thing. You got more mass. So yes, if I have more matter, I will have mass. But how do I measure that? I measure it on how hard it is to increase speed, decrease speed, or turn this. And I can link that. But the interesting thing is, it's not just that. There's something very, very different. And when we ignore this definition, you use the critical point for Einstein's warp space-time general relativity of 1915, 1916. You miss it. Chapter 0, all that crazy space-time stuff. You see, somehow, matter has mass. And that property of mass, what we measure how hard it is to increase speed, decrease. But we can also measure it a different way, and I'm going to show you that mass is what creates and feels gravity. It's a pulling force of sorts, without leaving Einstein aside, from one up. So if I had a super sensitive experiment, these two would be pulling. A would pull on B, B would pull on A. This would be pulling on me, I'd be pulling on it. But it's very weak. But still, if you get more and more, in fact, here's the punchline, and then let me show you that, and then we're done setting it up, and then we'll apply this to Newton's laws. You see, an object with more mass, I'll show that to you in a second. An object with more mass, what? Is harder to accelerate, and you know I don't mean just increase speed, decrease speed, or turn. But it also is pulled down harder by Earth. Earth pulls us down with the force of gravity. How can Earth pull so strongly? I can't pull that strong because it's got more what? More mass. Who has the mass? The matter has the mass. But mass, what is that? I thought I had keys in my pocket. I don't have any keys in my pocket. I got keys in my pocket, right? But what are keys? Matter has mass, but what is mass? Oh, it does two things, two very, very different things. Resist, okay, just go with that. We'll explore that. Now, let's go over here. Let me demonstrate it a little bit. And you have these concepts. Don't make it too big a deal. It is deep, but don't make too big a deal. Was that a bit of a weird glare in there? Should have done that. All right, so that's what I wrote. Pause it if you want. Okay. So to finish this off, let me show you mass in action, or not action, right? Resisting, whatever. Okay. Remember the spring. We're going to see how all this applies to astronomy. In fact, forget about doing astronomy if you don't have this. All right. Let's go with this spring again. I'm going to show you mass doing two things. Can you see that? Let's make sure you can. I'm going to take a spring. I'm going to take something. Now I could use these guys, but I'm going to use this guy over here. Okay. Set this up. This is what I'm showing you here is experimentation. Now, pretty sloppy, but this is the core of science, isn't it? What I'm going to do is stretch that spring the same amount both times. All right. Let's stretch that spring. It doesn't have to be too hard, but to figure it out, to realize this is profound. We'll get into all these other things in just a sec. Okay. So now watch. You can tell me whether it's a gentle, small acceleration or an abrupt, large acceleration. I'm going to take this and I'm going to stretch this a certain amount. It's going to pull on it and you're going to see that it increases speed. Now, if I add matter, somehow it has more mass. What is mass? It's how much it resists that. Here we go. Much less acceleration, right? You can see that, right? What happens if it's moving? Well, if it's moving along, if it gets moving, once it gets moving, it's easy to stop that. Kid on the skateboard, it's easy to stop then. Elephant on a skateboard that's moving, hard to stop them. It's got more inertia. Hold on, don't draw a conclusion quite yet. It's going to get a little bit tricky. Now watch this. So I saw it by changing its motion. I can also see it by turning it. How hard it is to increase speed, decrease speed, or turn. And if it's twice as hard, we say it has twice as much mass. There's something else before I want to go there. This. That's accelerating it. You can also measure mass with the other property, the pull of gravity. Ooh, that spring's got to pull up. We're already doing Newton's laws. If I double, if I have more mass, it's being pulled, the whole thing is being pulled. Why? Well, it's two things that are getting pulled. It's getting pulled stronger. How do I know? Because the spring has to pull up stronger, or my hand has to hold up stronger if it's got more mass. So I can measure that. In fact, scales, you can use how hard you have to push up to balance the pull down. And if you got more mass, you got to push up more than the pull down. Notice that that is not accelerating. So I can do it by accelerating, increasing speed, decreasing speed, or turning, or I can do it by balancing the pull down and see how much I have to pull or push up holding something. And that'll tell you how much mass there is. Interestingly, if you double this, you'll also double the resistance to increase speed, decrease speed, and turn. And that's a very different process, very different. No one understood that until Einstein. Not fully. Okay, Watch this though. You can clearly see I've added more matter, and you might go, well, isn't that more matter? Yeah, more matter is going to have more mass, but that doesn't tell you what mass is. I mean, you can see that, and if you're using the same material, then that's going to have more of that material, and this is going to be harder to increase speed, decrease our speed. Try throwing it, try catching it, right? That's easier. And this one's going to be less mass. That's true. More. But just because it's bigger, does it mean it's more? Let's check this out. This is much more than this. That's bigger, more space, more volume, we say. It takes up more space. Which one has more? Well, I can do that either by trying to accelerate it or by doing this guy, right? So here's a balance, Libra, equilibrium, equal balance, right? And I go like this. It's pulled down, this just has to push up to balance gravity. Oh, that one's pulled down harder, isn't it? Even though it's smaller. That's interesting. Okay, what about, clearly more. What about this? It's got more volume. What if I take out a little water? Just enough. Let's see what happens. I haven't. Still a little more mass. Why? Because it's pulled harder. It feels the force of gravity more. Oh man, here, perfect. A liter of water has a mass of 1 kilogram. All right, so we can measure mass these two different ways. Now, if they have exactly the same volume, do they have the same mass? No. Why? There must be more matter packed in there. Right? You can have more matter packed in. This has the same mass, whether it's packed in, less volume, or stretched out more volume. Right? So the size doesn't necessarily matter. And what's happening is, go back to those atoms, how many protons and neutrons are packed into those atoms, and how many atoms you pack in and stuff. So you can't see that with the naked eye. People didn't necessarily know that. So there you got a taste of matter. It's not the size of the thing, but something, if I go like this, if that's pulled harder, I know that if I grab that and throw it, it's going to be harder to throw than this is. It's going to resist accelerating more, and if it's coming towards me, it's going to be harder to stop. Now, not that much, but think of a truck versus a motorcycle, right? So, so that's it. If you have more matter, yes, you have more mass, but that hasn't told you what mass is. Mass is how much you resist increasing speed, decreasing speed, or turning. And if you double that amount, you will double how much it's pulled by gravity and how much it pulls other things. But that's very tiny. Okay, have we done it? Here, so here's an idea. Here's a container it's empty. It's got air in it though, so it's not really totally empty, right? It's got air in it, and that's got a certain amount. Now I can fill it, kind of like these guys. I can imagine filling it with sand, same volume. I filled it, of course that's got more mass. So that's gonna get pulled by gravity more, and it's gonna be harder to throw. And I can fill it even more, and of course like that. And that's gonna be harder to throw. It's gonna be harder and harder to throw depending on what you fill it with. That's it. Acceleration, force, mass, review as you need. Let's do Newton's laws.